Page 301, question number 1. A force of 125 newtons causes a spring to stretch to a length of 0.250 meters beyond its equilibrium position. What is the elastic potential energy stored in the spring? So we have a force of 125 newtons, and we have a stretch of 0.250 meters. It's asking what is the elastic potential energy stored in our spring. So the equation for spring energy is kx squared divided by 2. The problem is we have a force, we don't have our k value. So we have to go to our second equation, F equals k times x. So k is force divided by the distance that it's being stretched. So we have 125 newtons divided by a stretch of 0.250 meters. So I'm grabbing our calculator. We have 125 divided by 0.25 gives us 500 newtons per meter. So now we can go back up to our spring equation, put in our 500 newtons per meter. Our stretch is 0.250 meters, which we need to square, divide by 2. So 500 times 0.25 squared divided by 2 gives us 15.625 joules. So our energy is 15.6 joules stored in the spring. Part B, if the spring contracts to a stretch of 0.15 meters, so we're going to change it from 0.25 to 0.15 meters, what is the change in elastic potential energy? So to calculate our change in spring energy, it is our final spring energy minus our initial spring energy. And we have kx final squared divided by 2 minus kx initial squared divided by 2. Now keep in mind the k value is a physical property of the spring. So once the spring is manufactured, it has a k value and it keeps that k value until it is destroyed. So the k value will not change. We can use that 500 newtons per meter every time we see k for this spring. So we have 500 newtons per meter. Our final stretch is given as 0.15 meters. Divided by 2 minus 500 newtons per meter times our initial 0.25 meters squared divided by 2. So on the calculator, 500 times 0.15 squared divided by 2 minus 500 times 0.25 squared divided by 2 gives us a value of negative 10.0 joules. So it has decreased the amount of energy in the spring by 10 joules by changing the stretch from 25 to 15 centimeters. Now there's a second way to approach this question. You'll notice that in each of these terms we have a k and we have it divided by 2. So we can factor that out. So if we jump down here, we can say k divided by 2, and we'll have an x final squared. So x final squared minus our x initial squared, close brackets. So we'll have 500 newtons per meter divided by 2, 0.15 squared minus 0.25 squared, close brackets. So 500 divided by 2 times brackets, 0.15 squared minus 0.25 squared, close brackets, gives us negative 10 joules again. So just like we had with velocity, if you're going to do this factoring, make sure that when you factor your k divided by 2 out of both terms, that you are left with x final squared minus x initial squared. You cannot do x final minus x initial and then square the answer. You must do the squaring before you do the subtracting.